And we're back with another quick tutorial on oxygen not included. And today we're going to be tackling an issue I get asked about. Well, I've seen so many comments about it, but I've never really got around to doing it because it's kind of tricky to explain properly. And it's to do with specific heat capacity and thermal conductivity. The question really usually boils down to when you should use what, what's important for what, like insulation or transferring temperature. And today we're just going to do a very simple test to show you what each one does. So what we have here is obsidian on this side, and we have igneous rock on the other. Now the thermal conductivity in both, will, as you will notice, is both 2. However, the specific heat capacity on obsidian is 0.2 and igneous rock is 1.0. So igneous rock has 5 times the specific heat capacity. And the simplest way to think of specific heat capacity is, I'm going to use a battery analogy. It's how much power your battery can store. So this can store 5 times more power than obsidian. So what we will do is we're going to grab a bunch of magma. Now, it's not really hot magma, to be honest. It's pretty chill if we're going to be realistic. It's 2,000 kilos, but it's heated to 476.9 degrees. Then we zoom out a bit, and then we turn on the temperature overlay. You'll see everything's nice and green and balmy. No problems whatsoever at all. And in the moment we unpause this, it's going to get pretty hot pretty fast. So there we go. As you'll see, this here is expanding much more rapidly. The reasoning behind that is to do with the specific heat capacity. It only takes 1/5 the energy to cause this to heat up. So you've got, it's like having 2 batteries plugged into the same charger. They're both getting the exact same amount of power. It's just this one doesn't need as much power to fully charge or discharge. So it's got actually less energy in it. So if we check out here, this is up to 76 degrees. Over here, this has barely moved out at all. This will expand out and, well, take up 5 times as much space. Let's maybe fast forward time a bit here. I think that should be... Alright, that's gone far enough. Let's just have a quick check on something here. You notice this is at 20.9 degrees, whereas the adjacent tile is at 20 degrees. And then as this hits 21, you'll notice the adjacent tile, still no movement on it. It is still the exact same temperature. However, as the tile beside it goes just above 21, so say 21.1, which I should do now, there we go. You notice the tile down here, this tile just below it has gone up by 0.1 of a degree. So you notice there's a 1 degree difference between these two. And then if you'll notice there's a 1 degree difference between these two, and a 1 degree difference between these, and all the way down. So as you go back up, you'll notice it's just a 1 degree gradient going back up until you get a little bit closer. So there's actually a 1.1 degree gradient, and there's quite a bit more. What will happen is this will keep spreading out temperature again and again and again until eventually the whole thing is not one uniform temperature, but everything will be 1 degree warmer than whatever's beside it. Just an example of what will eventually happen. So this will just keep spreading out until there's just a 1 degree difference, and the exact same thing is happening over here. And it's fine, where is it? 20.7, and the adjacent one is 21.7. There's actually 2 adjacent tiles injecting temperature into that one. The difference will be, since this one over here has so much lower specific heat capacity, this will spread out 5 times as far. Now, it will also take a lot longer as well. You can see here this has been spreading out quite quickly. But just due to the fact that it takes so little heat for it to heat up a tile, it will just it will spread out over a far more distance, but eventually it will also end up the same, where each tile will be 1 degree different from the one adjacent to it, just covering 5 times the space. Down here, of course, we've got another little test. This is a thermal conductivity of 1, this is a thermal conductivity of 2. So this conducts heat way better, well, twice as well as this one. So with this great conductive material, 1 degree of difference between each block. This one, what are we guessing? We'll say 2 degrees of difference, something like that, before it'll exchange temperature. Let's inject some heat in here and find out. I have injected the exact same magma into both of them. Well, it's not really magma, to be honest. It's instantly going to turn into rock, but exact same temperature material for our heat injection. Then we'll just unpause it and let the heat spread. Okay, so what we should be expecting here is this one should transfer heat faster because it's got the better thermal conductivity of 0.2 over the or of 2.0 over this one, which has the thermal conductivity of 1. So this should transfer temperature at about half the speed. So you'll see this red blob expand much, much faster. Now we'll come to the practical applications of all of these particular features later, but for now let's just have a quick check and see how this works out. Alright, that's a bit of a surprise to me here, but it turns out, there's a 1 degree difference between the tiles before temperature will start to change between these two as well. Same this side. The only difference is this one's spreading the temperature far faster. It seems this just transmits the heat between the 2 tiles quicker, You need the exact same 1 degree temperature difference. I had always assumed that the temperature differential would determine how much of a heat difference you need before temperature starts exchanging. That would appear to be, that's probably a standard then. If, unless there's 1 degree of temperature difference between two blocks, they will never exchange temperature. Good to know. However, that's just a few of the that's just solid materials. What happens when you start introducing gas? Up here we have a container of 2 kilos of oxygen, and on the right of it, 2 kilos of hydrogen. They're rather large, but what we're going to do is we are going to paint in just a little blob of magma into each of those, exact same as before, the exact same temperature. Then we're going to check out the temperature overlay and see how it goes. Now, as you'll see, it sort of spreads out in a very similar pattern, but wow, okay, that goes... I was expecting that to go up, down, left and right in pretty much the exact same ways, but it seems it actually spreads out horizontally. Huh, very unusual. That might be because of the way I've got the tile set up. 1 second, I should have probably turned these into blocks. You know what, we'll let this run for a little bit longer and then I'll retest the experiment with making this a perfect square. Alright, I think we've got enough info there. I think the surprising part is how much it spreads horizontally. That is crazy far how much that spreads. We'll just kill off those igneous rock pieces. Wow. Okay, also as well as that, when it goes upwards, it seems to go far... seems to rise actually a little bit. 17 up and only about 11 down. Interesting. However, we should really check here. The temperature differential here is enormous, and yet it still travels quite slowly, despite there only being 2 kilos of gas for it to pass through. And the oxygen transfers temperature an awful lot better than it does the hydrogen. So it's got a specific heat capacity of 1 and a thermal conductivity of 0.24. Hydrogen in theory has much better thermal conductivity, but a much higher heat capacity. I thought with that enormous, I mean, it's 0.168 versus 0.024, so it's 6 times greater. The thermal conductivity of hydrogen is 6 times greater. However, gas just doesn't seem to transfer heat very well. Hydrogen is actually a better insulator than oxygen. That's... okay. You learn something new every day. I thought it would have been the other way around, but that's the way it works. There's a multiplier applied to the transfer of heat in gas. The reason being, otherwise you wouldn't be able to transfer heat very well. I mean, one tile of anything is usually 100 kilos. So a 100 kilo tile will have 50 times the mass of the gas touching it, which could lead to really weird calculations. So the gas has a bit of a multiplier for when dealing with heat, so that you don't, so that some actual heat can be transferred to it. Same experiment, but this time I put in a box just to see if it really is just spreading heat that horizontally. Yeah, that's immediately going all horizontal. That is rather surprising, though. Hydrogen doesn't seem to spread out the heat quite so fast as the oxygen. Good to know. One last test. For one final gas experiment, I changed it so that there's 100 kilos of hydrogen and oxygen in every tile. So it's the exact same mass as the stuff down here. And let's just see if it behaves any differently now. And no, just slower. Alright, that just gets even weirder. There's actually convection in this game. Never even thought it was possible. So yes, all of the hot gases appear to just travel up to the top, where they just, they don't really spread out their heat so much. That is, assuming you have really, really high gas pressure, that's what happens to heat. It just floats to the top. Great to know for the steam rooms. Oh wow, that is actually very pretty down there. I just did a little bit of investigation here. This is actually perfect. We'll see 26.9, 27.9, 28, 30. And then it drops a point of a degree right there. Then it just keeps going up at 0.8 right until it gets to just before here. There's one temperature difference in everything until it gets to that point. But I think that's more to do with these tiles beside it. For some reason, some of these are under a lower temperature of 0.2. This should be 50.8. Or yeah, 50.8, but it's 50.2 because some of the heat got drained into these tiles. I don't know exactly. But by and large, yes, you can expect a degree of temperature difference between tiles. Kind of amazing. And oxygen, it seems all the hot stuff just goes straight to the top and barely spreads any heat around. Who knew? Hydrogen, pretty much the same thing, though that's only if you have vast quantities of it. If you have it at just 2 kilos of pressure, it seems to just spread out nice and horizontally. Very strange. Anyway, let's move on. For our next little experiment here, I'm going to have to start calling them experiments. I've learned so much. I thought it was going to be a tutorial more of an experiment, but I suppose we learned at the same pace. This here is a tank half full of oxygen and half full of magma. 2 kilos of oxygen and about 1800 kilos of magma, though I may have pushed them up again a bit tight together. Now, if you look here along the outside, you'll see these insulated tiles are all 20C, and they're all obsidian insulated tiles. They're not the best, they're not the worst. And by not the best, not the worst, I mean their specific, where is it? Their thermal conductivity is 0.020. If you'll check them before, wait, we've got an obsidian tile over here, a regular obsidian tile. That one is actually 2. So these are far less conductive, and thermal conductivity with an insulated tag on top of it means that the only conductivity that is considered for transferring heat is the heat of the tile. Normally, if you have two materials, it's averaged out between what the thermal conductivity of each one is, and that works just fine. But when it's an insulated tile, the only thing that counts is the insulated tile's ability to conduct heat. However, you're going to notice here, these tiles up here are all getting nice and toasty. You'll notice they're 30-40 degrees, whereas these ones down here, they're all staying at perfectly 20 degrees. They don't care. They're bathing in two tons of liquid magma. And they're like, yeah, no, we're good. We got this. And these tiles up here are touching barely 2 kilos of oxygen, and they're getting toasty. What gives? Why are they transferring so much heat? Well, this is back to that multiplier I was talking about. Gas gets a multiplier for transferring heat into things. That is why these tiles are all getting heated up. Nothing really you can do about this, unfortunately. It's just the way the cookie crumbles. Oh, one thing here. Let's deconstruct that for the moment. Now, there used to also be a bug where pieces of debris, if pieces of debris were dropped on top of an insulated tile, the heat transfer from debris was preset and it didn't take into account the insulated tag. Therefore, you could end up with pieces of debris transferring temperatures into your insulated tiles. That has since been patched out, and debris no longer does that. So you don't have to worry about scraping every little piece of debris out of your perfect devices in case it accidentally overheats something. But this just lets you know, yeah, hot liquids, the insulated tiles don't care. It takes forever for them to change temperature. Hot gases, slightly different story. You might want to double insulate. Double insulation means, well, exactly what it says. Just put 2 layers of insulation. That will last you pretty much for an eternity and a half. The reason being, the 2 insulated tiles just will not exchange heat until one of them gets incredibly hot. You know what? Let's find out how hot it takes before the 2 of them will start exchanging temperature. Ah, there we go. This one's at 88, and this one here has gone up 0.1 of a degree. So it takes quite a temperature differential. Once the temperature got to about 120 degrees, we saw another 0.1 of a degree in temperature change. Alright, this is taking way too long. We're up to 0.3 of a degree that we had to get to about 150. I'm going to see if we can't speed this process along a bit. Alright, so the gas in here is now almost 10,000 degrees. That's pretty hot. As you can see, there we go. That's some proper temperature rise right there. Let's see how long it takes before it starts to transfer some serious temperature. After way too much time and 9,990 degree oxygen, I eventually removed that. We've got it up to 1200 degrees, and it's managed to raise the temperature of the adjacent insulated tile but up to about 5 degrees. Yeah, so double layering will pretty much prevent all heat escape from gas. I mean, unless you've got something that you're trying to keep really chill on the opposite side of this, I think you're pretty safe. When it comes to the liquids, they don't care. Liquids just don't really transfer heat very well to obsidian. Wait, was there one there? Oh, look, 21. Ooh, the only place that's happened is actually under the debris. It seems the debris is transferring a tiny little bit of heat, but it's not as bad as it used to be. Okay, so maybe don't leave debris in there? Well, that's a 1 degree difference. I'm not going to cry over that one. But yes, gases will heat up insulated tiles, just slowly. Liquids, they don't care, and solid-to-solid transfer is really slow, like incredibly slow. Next up, some practical testing of just what you can use this knowledge to, how you can use this knowledge to your advantage. First up here is, this is sort of the hot plate for this petroleum boiler. And I've always said you should make it out of gold. The reason being it has this very low specific heat capacity. That's the battery charge, or the level you can charge it up to. And the thermal conductivity is not too terrible. The reason having such low specific heat capacity is good is when you're injecting heat from here into here, this is sort of like the bottleneck, and you don't want to inject too much heat. If you inject too much heat, you're going to overheat the petroleum, and that's just wasted heating. You only want to heat things up to a certain amount. So what we'll do here is we'll just slow this down a bit, and just as those doors close, you see the heat starts to be injected. This temperature sensor is set to 403. Once it goes above 403, that door is going to disengage. But if you check up here, say in this corner, you can see the temperature's gone up quite high. It hits about 412. Yeah, it hit about a little bit over, about 412.5 degrees. So it's overheated by just a little bit. But then it starts to plummet down again. Now that's if you're using a gold temperature shift plate, or a gold, sorry, not a gold temperature shift plate, a gold metal tile. However, we'll go down here and you'll notice this tile is made of copper. Now, copper has the exact same thermal conductivity, but the specific heat capacity is not 0.129. Instead, it's 0.385, which is, well, that's over twice as much. What'll happen here is once this starts to inject heat, which is right there, you can see the temperature goes up and we get, actually 414.9 it peaked out at. The reason being there was more battery to draw on, even though it's only a very small amount, and I know there's lots of petroleum in here, this is the bottleneck. The heat from this door, well, magma through temperature shift plate into the diamond window tiles, temperature shift plate from the diamond window tiles into the door, and from the door, those two are just touching. There's no temperature shift plate between them. So this sort of acts as the bottleneck and slows down how much temperature can get transferred. Now over here, well, yeah, let's just say we went a bit crazy. This one has even better thermal conductivity and a massive specific heat capacity of 0.910. So let's see what happens when this one engages. And there we go, temperature starts to get injected, and where do we peak at? 117, 118, yeah, about 118.6. Ooh, 0.7, 418.7. The reason being, it's not even to do with the thermal conductivity so much as the specific heat capacity of this tile is allowing more and more heat to be injected. So I've got these three set up. I gave them all fresh magma at the exact same time, and let's let them run a bit. And when I say run a bit, we're going to run them until they actually run out of magma, or until the magma runs out of temperature to inject, and then we'll know which one runs out first. Now the temperature differences, or the difference between all three is not going to be massive. The reason being, we're dealing with a lot of magma here, and only a few degrees doesn't make that big of a difference, but it does count for a few things. For example, overheating your petroleum will mean as it flows back out of here, you've got a chance of overheating the incoming crude oil and causing overheats and stuff like that, so sometimes it's nice to know exactly how much you can push things. And we've run out of heat. Well, this one has. This is the aluminum tiles with the very high specific heat capacity, and you'll notice here the temperature has dropped to 443 degrees, and it's ready to cycle out that magma. Over here, the copper here has a lot less specific heat capacity, and it's at 480 C. So it's got about 40 degrees more temperature in it. Then if we go up here to the gold, which is slightly better at 0.129 for its specific heat capacity, you'll see we've actually got 490, about 10 degrees more. Now, as a bit of a side project, I messed around. These diamond temperature shift plates are very good for transferring temperature and very cheap and efficient. But over here, exact same gold tiles, but I've replaced the temperature shift plates with gold temperature shift plates, smaller specific heat capacity, just to see if it made a difference. And the temperature over here is actually 510. So we were able to save a little bit more heat as well by using slightly more lower specific heat capacity temperature shift plates than using the diamond ones over here. So there is a way to actually make this even more efficient, but it just costs you a lot more gold. I'll still stick with diamond for the generic build, just on the grounds that diamond's easier to acquire, but if you're looking to optimize things even further, there's ways to use specific heat capacity and thermal conductivity to your advantage. Let's have a quick look at temperature transfer, because there's one thing that's very often overlooked is temperature is transferred just on the four cardinal directions. So if we check the temperature overlay here, these three tiles totally heated up, but the ones right here, diagonally touching them, nothing's happening. And that's sometimes inconvenience, and it's where temperature shift plates come in. So what we can do here is, you know what, let's sample it over this side. If we were to say paint this in there, you'll notice that's insulated ceramic tiles, and the rest of this place just remains nice and balmy. Absolutely no change in temperature anywhere because it can't get out. It's trapped inside these four tiles, no temperature exchange possible. However, we stick in a diamond window tile, that exchanges heat with all 9 surrounding tiles. So even these corner pieces, that quickly turns the entire place into an incineration zone. And that is the joy of temperature shift plates. However, they do have a few limitations. So, for example, we can paste it in there. That's great. It shares its temperature with the adjacent temperature shift plates. However, those temperature shift plates don't really seem to share temperature with each other. That one's actually gaining a little temperature because it's sucking out of the ceramic tile here. Also, these temperature shift plates can force temperature into things that wouldn't normally accept them so quickly. So, for example, this ceramic is actually getting heated up, but it's not the magma that's doing it, it's the temperature shift plate is pushing it in. Temperature shift plates have sort of like a multiplier for allowing them to add temperature to something, just makes it very useful. Now, what you can do, though, is you could just, alternate stuff. If you put things in a daisy chain, that will heat that temperature shift plate, which heats that diamond window tile, next temperature shift plate, blah, 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 all the way along. And it allows you to just basically make a heat spike all the way. Also, I'm using a lot of diamond here. I know you can use other materials. It's just diamond happens to be incredibly cheap, plentiful in the oil biome, has a good specific heat capacity and amazing thermal conductivity. And there's pretty much no other use for it. So temperature shift plates and diamond window tiles seem to be its #1 focus. Another thing about this is, it doesn't really matter what medium it's in. If it's in any medium at all, that will also help transfer the temperature. So if you check here, and pow, it just, like, you can see it just rockets along the temperature shift plate line. These areas down here are still, what, 26, 27, they're barely touched, but up here, yep, 200 degrees and such. That's just a handy way of making sure temperature goes where you want it to. And one of the handy things about temperature shift plates. But now let's go and combine all that knowledge to make some cooling. What we have here is a probably oversized cooling device. I've made several like it before, but this one, just more for demonstration purposes than cleanliness. This is an oxygen production facility. In full Rodriguez, it's producing 3 kilos of oxygen, well, a little bit under, but it's about 68 degrees. It's coming out at almost 70 C. You can, of course, use radiant liquid piping going through here to help dump off some heat. There's other ways you can cool this, but we just want that as hot as possible so we can demonstrate things as efficiently as possible. This here is just regular granite pipe. We're going to connect them up here. And, we're going to sever those right there. And if we've done this correctly, everything should now be passing through this direction. And you notice here, this is heating up the pipe slowly but surely. 50, 40, 40. Comes out the other side though, and it's actually dropped quite a bit in temperature. The reason being, the granite here is passing through this section. It's a nice, chill tank of liquid, water. And the water is cooled down to about 7 degrees, was it? Yeah, it's all cooled down to 7C. And there's some temperature controlling we'll go into in a bit. But what's important here is these granite pipes, they're not special. They're just regular, standard issue granite pipes that you can build at the start of the game. And you'll see the gas here is going in here at 67C at one point and coming out at 46C on the other. So you're losing some temperature, but it's 7C in here. We should really be losing an awful lot more. What would happen if we were to replace those pipes with, say, radiant gas pipes? After installing the radiant gas pipes, you'll see here oxygen's coming in at 60, going out the other side at 27, 27, 27. That's a hell of a drop. Now, it's not down to the 7 degrees, but it's to do with, well, radiant gas pipes. Radiant gas pipes are an annoyance because you really have to sort of compare them to liquid pipes to get an idea of what's going on. This is them all compared off against each other. However, there's a bit of a difference going on here. When you're making ventilation pipes, they can only be made out of ore. Well, that's a rough rule of thumb. There's exceptions. So you've got gold amalgam ore is what you're making your radiant gas pipe out of, which is why it has such terrible thermal conductivity. Whereas you make your radiant liquid pipes out of refined material, which means it's made out of actual gold, which means its thermal conductivity is absolutely amazing at 120. So gold amalgam is the worst for gas pipes, but actually one of the best for liquid pipes. It's very confusing. Until you actually look up the numbers, you don't realize what's going on. For example, iron here, thermal conductivity of 110 for liquid piping. For gas piping, 8, and it's come in second. Then copper is 120 for liquid and 9 for ventilation. It's just weird. Tungsten, well, wolframite refines into tungsten. Wolframite is actually quite good for gas pipes and is, unfortunately, it's pretty rare though. So you don't really usually want to waste it. And it also makes a good radiant pipe. Aluminum ore is probably one of the best ones. You'll see here it's 41 for aluminum ore for a gas pipe, and it's really great, and it's even better for liquid pipes if you're trying to exchange temperature. So this is probably one of the best materials for temperature transfer in the game, unless you want to start getting into space materials. For example, we've got niobium up here, or thermium at 440 in both. It doesn't matter if it's used as a gas pipe or a liquid pipe. That's because these three up here, these three are all refined materials. So steel is also pretty good as a radiant gas pipe. It's actually one of the best. It's the third best in the game. Also very expensive to get your hands on. Also makes a decent radiant pipe, though not as good as, say, something like gold, which is much cheaper and easier to get your hands on. So I suppose for the big takeaway would be for your gas pipes, use aluminum ore or steel if you can. That's actually the best one to use, and you usually only need small runs of it. For your liquid pipes, I find gold is usually sufficient, or even copper. So copper here is 120, gold is 120. Aluminum is wonderful, it's just, depending on your map, you may not have access to it. But down here, we made these pipes out of copper ore. And that means we're getting some decent temperature transfer. We've knocked it down to 26, but we've got the potential to take it down to 7. Now, another thing you could do is you could extend out this temperature transfer area, so there's more area to transfer temperature. But let's just see what happens when we put in some better gas piping. I say we switch to aluminum. With aluminum, we're getting it all the way down to 7C. Would you look at that? Oop, that one's at 8, that one's at 8. Okay, they're a little bit further down inside the tank, so oh no. It's working out pretty good. That was a difference of, let's see here. That was 9 thermal conductivity on this copper ore pipe. This one up here was 41. So that much of a change really allows you to get much finer control. Now, one last thing. Sometimes it's just better to throw things at a problem rather than try anything too subtle. So down here you notice we've got a giant tank of water. That giant tank of water is hooked up by a temperature sensor to these doors. And these doors are sucking temperature from this big ice block over here, fed by a super coolant powered aqua tuner. A little bit of late game design, I'm going to admit. However, the reason we're using water down here is it's just massive thermal capacity. If we just go in here to the water itself, its specific heat capacity is 4.179, which in comparison to say something like oxygen over here, that has a specific heat capacity of 0.790, and we're only passing through a kilo of oxygen per pipe, whereas there's 1,000 kilos of water down here. This just allows you to keep things stable. For example, if we were to swap all of this out and change it for, say, hydrogen, there we have 100 kilos of hydrogen. Now, you probably wouldn't be able to achieve that quite normally in your game. The reason being it'd be too hard to get 100 kilos in there. I suppose door compressors, you'd probably only have 10. But just for example here, you look over this side, it is bringing out the temperature, but it's not nearly as stable anymore, and it's going to fluctuate up and down a lot. Some of them here are 5, some of them here are 6, and as the temperature goes in and out, you'll notice them going up and down constantly. It's just, there's not as much mass in there to keep a stable temperature. It gets even more pronounced if we reduce this to 20 kilos. 20 kilos is what you can reasonably expect to put into a room without using some sort of exploitative bugs, or, yeah, well, depending on what way you want to do it. And you notice here the temperatures are now going down sometimes to 1 degree, sometimes up to 5 or 6, 7. It's all over the place. It's not nearly as stable. So sometimes you don't need to put in fancy controls or the perfect materials, just throw a large quantity of mass at it. If you're trying to stabilize something and keep it at a very accurate temperature, just throw a lot of mass at it and just try and manage the temperature that way. Now, one last thing, let's go through some of the more useful items in the game for their thermal capacities and conductivities and such like. The worst gas for conductivity is chlorine. It just has the worst, 0.008. It's just useless. Hydrogen is one of the best gases because of its very high specific heat capacity. It's about half that of water. And water is very handy because of its very high specific heat capacity. It's the biggest battery in terms of heat. Then you've got polluted water. Also amazingly high specific heat capacity, and its advantage though is its freezing point is higher, or it can go to colder temperatures before freezing and higher temperatures before boiling. An extra -20 and an extra +20 on each end of the spectrum, meaning it's really good to use as a coolant because you can cool things down cooler or heat them up hotter before things start to break. For example, this aqua tuner over here, it reduces the temperature of the liquid passing through it by 14 degrees. And that's a flat 14 degrees, regardless of the liquid. So, if it's water going through it, it will reduce its temperature by 14 degrees, but that's 14 degrees multiplied by 4.179. If you were, say, to put through, though, supercoolant has a specific heat capacity twice that of water, twice as much battery storage power. And if that's reduced by 14 degrees, that's pretty much twice as much cooling you're getting out of it, all for the exact same amount of power. That's why supercoolant is so useful, and why polluted water is so useful. Now, I'm giving an honourable mention here to ethanol. Don't really use it much myself, but it does have a huge thing going for it. It can go down as low as -114 degrees. Its vaporization point is a little bit lower, but it does mean you can freeze things quite chill very early on with access to ethanol. However, its specific heat capacity is much lower, 2.46. It's not quite half of water, but let's just say it's much weaker, meaning you'd have to run this through your aqua tuner an awful lot more to generate as much cooling as the water would do. It just has the advantage of being able to go down to lower temperatures. I know this tutorial was not your standard fare with a specific build in mind. It was more just about a lot of general questions you get asked about temperature transfer and how it works in this game. I learned a few things though. I didn't realize oxygen did actually have a bit of convection. Well, I'm assuming you have enough of it, and that gases spread heat horizontally more than vertically. Oh well, you learn something new every time you start playing around in this game. I'm going to leave you with this, which is a block of half obsidian, half igneous rock. The igneous rock has a specific heat capacity of 1. The obsidian on this side has a specific heat capacity 1/5 of that. So this should spread temperature far faster, this far slower, and we've stuck a big blob of magma in the middle. And we're just going to time-lapse that for the credits, just make a wild guess as to what you think is going to happen. Anyway, I hope you enjoyed, and good luck. Wait, this makes no sense. The hottest part is no longer the center where all the heat was injected. The hottest part is now a few tiles to the left where it's 47.4. How is this now hotter than the place where all the heat was dumped off? What? Like, wow, this game always finds new ways to surprise you.